Today, I'm going to talk about a series of quite serious emergencies that can have major health impacts. This is the second in a series of lectures on major emergencies with health implications. The last one was on nuclear, radiological, and chemical issues. I will subsequently be doing one on major weather events. But today, I'm going to be talking about literally when the Earth moves, earthquakes, volcanoes, and tsunamis. And these can have devastating impacts on communities, really essentially out of the blue.
The Gresham College lecture that you're listening to right now is giving you knowledge and insight from one of the world's leading academic experts. Making it takes a lot of time, but because we want to encourage a love of learning, we think it's well worth it. We never make you pay for lectures, although donations are needed. All we ask in return is this: send a link to this lecture to someone you think would benefit, and if you haven't already, click the follow or subscribe button from wherever you're listening right now. Now, let's get back to the lecture.
Earthquakes and tsunamis and volcanoes can be highly destructive. They tend to have immediate short-term effects, which will happen in the vicinity of the event. They can then have much longer-term effects, which cause impacts even down generations. And if we want to respond effectively to these events, we have to understand some of the basic science behind them. Now, those of you who've most recently been at school will probably have a better understanding of this than many other people, but I'm going to go through some of the basics of this because I think it explains why it is that particular events tend to occur. Firstly, when thinking about earthquakes, volcanoes, and tsunamis, particularly earthquakes and volcanoes, where they're likely to occur is largely, though not entirely, predictable. They'll tend to occur along lines where tectonic plates meet one another. These may be major ones, as in this map, or they may be more minor ones. But they occur in particular geographical areas. And I'm going to start off with earthquakes, because earthquakes are the most frequent and cause overall the largest number of deaths, but there can be some very major examples of the other two, volcanoes and tsunamis. A very large number of the major earthquakes that occur in the world, in fact, occur a long way away from land. They occur out in the sea and have no practical health implications. So there are a lot of earthquakes occurring that are really quite major, and they're the dots you can see on this map. The basic principle of an earthquake is relatively simple, although there's a lot of complexity lying underneath that. Two plates are moving in different directions, usually quite gradually. And the land between them is locked. It's locked in place, essentially by friction. And then at a certain point, the stresses grow and they grow and they grow, and at a certain point, they suddenly move. That sudden movement, where they kind of release that energy, that is what causes the initial earthquake. So that's the initial event. They can occur up and down, side to side, a variety of ways they can occur, but they all have this basic principle of a sudden release of stress that has been building up over years, decades, or even centuries. And it's suddenly released in one go. The geology of earthquakes is important, and it's not just usually a single line. They can occur at different depths, and you can often have lots of different fault lines running in different directions, and these have implications as to where the earthquake is going to go to, and therefore what the effects on health are likely to be. So on the right here, I've put the geological sort of cross-section of an area of the Himalayas. I'm going to talk about this later in Nepal, where a major earthquake relatively recently occurred. And you have to think of it, in a sense, in three dimensions. Earthquakes can occur in many places in the world, and most of them are so small that the average person can't feel them, or as described here, this is from the 30th of January this year, in the island of Mull, someone felt that it felt like someone had driven a car into their house. And if you've been in a place with an earthquake, and some of you probably would have been, it's an extraordinary jolting feeling, very disconcerting, actually, when it occurs. On the left here, I've put the earthquakes that would have occurred in the 60 days up to last weekend when I finalised this particular slide. Just demonstrating that, in fact, even in the UK, which is not an earthquake-prone zone by any global standards, we are having constant small earthquakes, which essentially no one notices and do limited or no damage to either people or property. So the earthquakes we worry about are the much larger ones. And here what I've put up on this slide is just some of the earthquakes that have occurred since 1970, so just over the last 50 years. And I've done that, and I'm not going to read them out, just to show what an absolute disaster earthquakes can be. So since the turn of the last century, 1900, it's estimated that somewhere between 2 million and 2.5 million people have died of earthquakes. And these significant earthquakes are occurring every few years. So just read those numbers to get some sense of scale. It is possible with current seismological science to work out where severe or moderate earthquakes are at least potentially likely to occur. And this is a map of Europe. We could do the same, mapping it out in different areas. The darker the red colour or purple colour, the more likely a severe shaking of the ground due to an earthquake could be. And as you can see, quite large areas, for example, around Italy, Greece, around the borderline of Spain, are potentially earthquake-prone. And we do, from time to time, have very substantial earthquakes in those areas. It is, however, almost impossible to say with any kind of forward accuracy when these earthquakes are going to occur. And usually, if people get any warning at all, it'll be warning that is a very short period in advance. And I think one of the mistakes people make is thinking you can predict when they will occur. You can predict where, but you cannot predict when they will occur. And I'm just making the comment because in 2009, there was a major earthquake in Italy. It caused a lot of destruction. And in that, some of the scientists had given some possibly slightly incautious advice, but people said they should have warned them that the earthquake was coming, and they reassured them, and they were sued for manslaughter, and they were jailed because they'd not been able to predict this. Most scientists would say this was asking for an impossible question. You simply cannot predict in advance when an earthquake is going to occur with any degree of confidence. And you can see down below there the major earthquakes that have occurred in exactly the same place. And they are usually many years apart, but not in a predictable cycle. Now, from a health point of view, there are immediate, medium-term, and long-term effects on health. And I'm going to intersperse the science of the earthquakes, volcanoes, and tsunamis with the health impacts of those, because in a sense, that's the bit which really I, as a doctor and public health person, am wanting to respond to. The biggest immediate risk in terms of numbers of people is usually from buildings collapsing. You essentially have a large number of people in a concentrated area with lots of masonry on top of them, and it falls down. And the implications of that, in a sense, are obvious. People get damaged, have trauma, and they get buried under the rubble. There's a much lower risk for people who are out in the open. So if you're in the open with an earthquake, although it's scary, actually the physical risks are much lower. They're not zero, but they're a long way down. But things that are natural can still fall down. Cliffs can release, as I'll show, rubble, trees can fall over. You can have damage from people falling over in particular areas. Those, in a sense, are obvious. Less obvious, but a repeated risk, is fire. Any city that has got gas mains and sources of sparks can have those ruptured in multiple places, leading to catastrophic fires. And if you look back, for example, to the earthquake of San Francisco in 1900, a very major earthquake, and further ones will occur in San Francisco because of where it is. Actually, the majority of the damage was caused by fire rather than the earthquake directly itself. So fire is a secondary risk, with a risk, obviously, to humans of burns. Now, if you are in an earthquake area, it's worth just being aware of this simple memory thing that you should drop, cover, and hold on. This advice is given in anywhere that speaks English. This is the standard advice for earthquakes. Drop to the ground. That's because you're going to be swaying around. You may fall over. Just get yourself down to a place where you're safe. Cover means under something which is ideally moderately robust, but as you can see with these children being trained, a chair, if that's what you've got, will do, desks, tables, something reasonably sturdy, so that if masonry falls, that the fall will be to some degree broken or stopped completely. If you can get into a room with no windows, that is safer than one with windows because it's stabler in terms of its structure, but you're actually safer if you're outside. So if you're just going into a house, get back out again and stay out in the open. It's very important to understand with earthquakes that although there will be an initial shock, there will almost certainly then be aftershocks. So the first one is not the last one, and as I'll come on to, may not even be the worst one. Now, how much damage we'd like to get from an earthquake depends on a number of factors that are broadly predictable. The first of these is the strength of the earthquake itself. And this is really determined by a number of things, but in particular, how much energy essentially has built up and then is dissipated through the earthquake. So some of them are much stronger than others. The way of measuring this, the most well-known scale that is always referred to in the films, is the Richter scale, but actually there's some slightly more updated versions of the scale. In a sense, these don't matter. What matters is to understand these are logarithmic. What that means is that 6 is a lot worse than 5, and 7 is a lot worse than 6, and so on, up the scale. So if you get an earthquake that is below 5, the probability of severe damage doesn't mean that it's 0, but is really quite low. If, on the other hand, you have an earthquake that's got a magnitude of 7 or greater, widespread damage is highly likely, and they can go up from there. The next thing that can cause problems is aftershocks. And I'll go through this in some care because they have big implications for what you can do in terms of response to it. The distance from the epicenter is important. So the further you are away from the epicenter, generally, the lower the impact. But again, that's very variable. And then there are some other geophysical things which include how deep it is, its amplitude, what kind of speed that the quivering is happening, whether the soil liquefies. If you have been on a beach and tried to shake sand, for example, sometimes it liquefies. The same thing can happen with an earthquake, meaning that can destabilize buildings, even ones that have got quite solid foundations. These are all factors that are factors of the earthquake itself. But then there are two human factors which are at least arguably more important. The first one is building design. Some buildings are much more likely to stand up in an earthquake than others, particularly if they've been designed to, but even older buildings, there'll be a lot of variety. And then, unsurprisingly, population density. A very major earthquake in a place with a few cows is much lower risk to health than a slightly smaller earthquake that happens in the middle of a city, particularly one which has got relatively limited building control. Now, I'm going to illustrate some of these things with an earthquake, partly because I was very peripherally involved in the response to it, so I knew quite a bit about the details, but I think it also demonstrates many of the key factors to understand about an earthquake. And that is the tragic 2015 earthquake in Nepal, and many of you will remember that from news reports of it. It was a 7.8 earthquake, so quite a large one. And in terms of the scale of damage, it caused around 9,000 deaths, so a lot of people dying very suddenly. It also injured about 22,000 people significantly. I'm not talking here tiny grazes and things. And it rendered houseless and homeless over 3 million. So this is the kind of size of impact you can have on a country when an earthquake occurs. Now, in terms of our understanding of the tectonic area, the seismology of this area, a lot was known about this. The seismology of the Himalayan area has been very heavily studied by many excellent scientific groups. So the understanding of all the kind of stress features, where the various fault lines are, is really very strong compared to some other areas. And Kathmandu, which is the capital of Nepal, we'd known was likely to have an earthquake, and there are many other great cities that are likely to have a major earthquake for some time. So there was no surprise that an earthquake was going to occur in this area. Tehran, for example, might be another city where that is likely to occur. What then happened is you have the beginning of the earthquake on the left of this map, and it spread in a kind of wave all the way down to the right of this map. And what essentially was happening was this is an unzipping down the line very, very fast of the two plates that are locked together. So that's how it works. It's an unzipping in one direction or another, and it moved, in this case, from left to right, causing shaking all the way down as it went. The epicenter was quite a lightly populated area, but halfway through that line was Kathmandu, a very heavily populated area, and a lot of the initial damage was caused in the city. Now, at the end of that, lots of seismologists studied it immediately, got quick hit out immediately, and their immediate estimate was roughly half the energy that was stored in that stress line had been dissipated, had gone away. What that meant was one of three possibilities could occur. Firstly, it could just gently ease itself down to release all the rest of the stress over the next few days, causing essentially no major new earthquakes, minor ones. Secondly, you could have a second earthquake of the same size as the first one. And the third is essentially between those two. You have a series of smaller earthquakes that dissipate the energy over a period now that that stress line has essentially become less locked together. So we knew that almost immediately, but how deep it was, its epicenter, how many shocks had very significant impacts on what was going to happen next in terms of human health. So the earthquake, as I say, propagated left to right over time, and at the end of it, in the areas in blue, the stress had gone down a lot, and in the areas of red, it had actually increased to some degree. So this is the changes that seismologists, who are the scientists who study these kind of things, were able to tell us about at a very early on, meaning that we could predict what was the upper end of future events immediately after this. Now, after this first earthquake, the first big quake, which in this case was the biggest, but it's not absolutely inevitable, there were multiple aftershocks. And I think it's really important to understand the importance of aftershocks because they have both physical and psychological impacts. The physical impact of these is an area that's been badly shaken and often damaged is hit again, potentially repeatedly, by more shocks, knocking down buildings that have become weakened in the first shock. So all the damage isn't necessarily on the first day. In fact, you may have a lot which is in other areas, and they can occur towards the leading edge. They tend to occur at the far end of the unzipping that I talked about previously. So in this case, most of the aftershocks were at the far end on the right of this map. That was the direction of travel. Had the earthquake gone the opposite way, it would have been in the opposite direction. They can be very destructive. They can have a big practical implication. So, for example, if you're trying to dig people out of rubble, and then there's another shock, that can make it both dangerous for them and for the people responding. It also has a big psychological impact. People who've seen buildings flattened around them, they can't have a feeling of, right, well, that's over. I've now got to rebuild. We've got to just because more events are going to occur and they could actually be very severe events. So it actually makes practical implications much more tricky, and it definitely complicates recovery. And on the bottom here, what I've shown is a graph showing that the first big quake occurred on the 25th of April, and then there were a series, each one of those yellow dots is an aftershock. The higher it is, the bigger it is. And then there was a second really major aftershock, almost essentially a new earthquake, which occurred on the 18th of May at the far end of the unzipping. And a lot of the damage, in fact, was caused by that second aftershock. This then means that you can have immediate effects, but then delayed effects. So the immediate effect of buildings falling down, but you may then have a secondary effect as things fall away when there is further shakes that occasionally or frequently occur afterwards. And these can cause landslides, and that's even more likely if you've got a lot of rain, which actually essentially loosens up gravel and other areas. You can also get a situation where two earthquakes, or an earthquake leads to two landslips or one big landslip, leading to a temporary dam at the bottom of a valley. Water builds up beneath that, and then weeks or even months later, that dam bursts, flooding the area below it. So you can get a whole series of physical effects which are delayed. Mapping these out is very important, and to some extent, the damage can be predictable. And the reason for that is that the big landslides will occur where there's a very steep gradient. So a lot of the initial damage of the earthquake was caused on the flats, because that's where the big earthquake was, that's where the large cities were, but a lot of the subsequent damage was caused in the mountains, because that's where the cliffs are, and that's the areas which can then geographically collapse. And you can see on the right, this is from a journal in 2015, you can see the difference between before and after the landslips that occurred in one of these collapses. So you then have, you've got the earthquake, you've got the aftershocks, and then the third thing which can occur is a change in the weather. And in South and Central Asia, as in much of the world, there's a heavy monsoon that is relatively predictable in terms of its timing. And the earthquake occurred before the monsoon. So you had the earthquake, you then had the aftershock, and then the monsoon started the following month. And the monsoons in Asia are very heavy, the rain is very heavy, and as a result of that, you end up with landslides and destruction, which actually, essentially, the shaking has damaged and weakened areas, physical or man-made, and then you end up with these, and you can also get problems of exposure because of the weather becoming much more adverse. So these are all later effects you can get as a result of change in the weather after an earthquake. Now, what were the factors that were important, both positive and negative, on the tragic destruction and loss of life that happened in Nepal? Here are some. It was a relatively shallow earthquake, as earthquakes go. That had quite big implications for how strong it was and its amplitude, among other things. Kathmandu was built on sediment, and this led to a particular kind of waveform that meant that some buildings fell down and others did not. And if you look at photographs from the time, you can see some buildings that look almost intact, and next door to it, a building that's collapsed. That was to do with the amplitude of the wave that was passing through. The epicenter was rural, but as the wave propagated, it went through very populated areas. So that's a human factor. And then there were two things which, this was a tragic and appalling earthquake, but it could have been even worse. It occurred on a Saturday, so schools were not in place, and I saw many schools that had collapsed. Had children been there, they would all have been killed in the rubble. So that was at least one small mercy in this. And it was daytime, so many people were outside, who, if it occurred at night, would have been inside when buildings collapsed. So these kind of quite small changes can have the same earthquake can have very different impacts in terms of the effect on loss of life and damage to humans. Now, after the initial quake, there are some immediate priorities, and then you need to think about the longer term. In some kind of order, The first is trauma, things falling on people, people falling out of high buildings, whatever, trauma of different sorts. Any of you who've done a first aid course will be well aware of the kind of things you'll be talking about. Broken bones, very serious damage in terms of people hitting things or things hitting them. There's then a large need to search for survivors. Many people will still be alive but buried under rubble. And there is a lot of scientific and engineering expertise, which tends, when there's an earthquake, people will fly in, bringing in expertise, radars, heat-finding areas, dogs, which are very good at sniffing out whether people are there, acoustic devices, and then very, very clever and dangerous engineering to remove rubble from people whilst aftershocks are going on to try and remove them from danger. So this is a whole area of engineering science, disaster recovery, where there's a lot of international expertise around the world, including the UK, actually. Clean water is a really serious risk because water mains will have been fractured, lots of sewage works will have started flowing into the water area. So actually getting people drinking water is an immediate priority. People can die very quickly of dehydration. If it occurs in winter, shelter is very important. Lots of people's homes will have been shaken down or will now be so unstable that it would be very dangerous to have them living there as aftershocks carry on occurring. And then alongside this, all the systems of the state, all the systems of the private sector will have stopped working. So food, schooling, health services, the rule of law, all of these simply stop. So society is essentially frozen in time for a period and will be overwhelmed. And then finally, transport in and out may be very difficult. So if there's only one airport, for example, the airport may itself have been damaged, so all the international teams may have significant problems getting in. So there is sort of larger issues in terms of disaster relief. Immediately, in terms of the slightly narrower view about how you consider healthcare needs, here are some of the things we need to consider. Fractures, ordinary and more complicated. Soft tissue injuries and wounds, so when people have got very torn ligaments, for example, other damage of that sort. Burns, if there have been major fires, as there was in San Francisco, will be a significant priority. And if people have had major burns, these are complicated to manage and dangerous for the people involved. Inhalation from dust kicked up may cause quite a lot of damage in the lungs, and that may include many quite dangerous building materials. And head injuries, which are always complicated to manage, even if you have quite good systems with CT scanners that are working, MRI scanners that are working, which in this situation you will not. Something which is particularly likely to occur in earthquakes, not in other environments, is what's called crush injuries. And that's when the tissues have been crushed under a lot of weight and then are potentially suddenly released. And several things can occur which are relatively specific. The first of which is shock. Shock is when your blood pressure suddenly drops, and that's because a lot of fluid is leaking into the rest of your body. So people can get shock very easily. When they're pulled out of the rubble, the shock can set in. Because a lot of cells have been destroyed and crushed, you can get electrolyte imbalances, salts, potassium, sodium, calcium, going up or down in large numbers, and that in turn can lead to heart rhythm problems and cardiac arrest in some cases. Crushing of muscle tends to cause damage which damages kidneys, so kidney damage tends to be quite common after these crush injuries. And then there's something on legs and arms called compartment syndrome, where you get swelling, and that can lead to the viability of the limb being damaged. So a whole bunch of things can happen. Even when you've rescued someone, they can be left with very severe or life-threatening injuries from these crush injuries. In the medium term, after you've done this, there are then a series of predictable next steps. Loss of water and sanitation is almost invariable after a major earthquake. And that, in medical terms, means, firstly, obviously, you've got to deal with dehydration, but then immediately after that, you've got to think about sanitation. The major diarrheal diseases are much more likely to suddenly occur. And just to use an example of the appalling Haiti earthquake in 2010, Some cholera was imported into the country as part of the relief effort, actually, as it happens, in a very fragile system after an earthquake, and led to large numbers of cases and of deaths. You're going to get crowding, because people will have to crowd into the small remaining number of places you can live, and you'll get pooling of water, and these are ideal environments for respiratory infections and vector-borne infections, mosquito-borne things like malaria, if you're in the right part of the part of the country. And then there'll be a big breakdown in all the preventative services, all the curative services of the health system, and they'll happen suddenly. So all the things that were previously protecting people will suddenly stop. You'll get malnutrition if people are short of food, which they often will be, and exposure if it's the wrong time of year. So these are predictable, and you have to plan for them from the moment you know that one of these has occurred. To get the kit in, to get the response in. It's a different set of challenges to the engineering challenges of getting people out of destroyed buildings. And then you have the long-term health effects, which can last months to years to generations. Large numbers of people will have their livelihoods destroyed in an instant. Their shop, their farm, all their cows, whatever it might be, destroyed suddenly. And this can be multi-generational, not covered by insurance, as for example. Exploitation happens after all emergencies and is a big risk. You have to watch for that very carefully in the immediate response of almost any disaster. There will be a big step backwards in health services for a prolonged period of time, and if you're in a fragile country, that can have an effect over decades, where health service has been built up over decades, suddenly goes backwards in terms of its ability to respond. And there will be big psychological harms to many people. It's quite scary living in a city which has had a big earthquake, multiple earthquakes, and now you're living there again. This can have significant psychological effects. And of course, the longer term effects of things like vaccination being broken down. It is possible, however, to do things either before an earthquake or after it, significantly to reduce the risk that it's going to cause massive loss of life, but you can never take that risk down to zero. But you can reduce it very significantly by planning. The first thing is to work out where earthquakes are likely to occur, and then within them to do things like planning all the routes from the airport to the emergency services, where all the hospitals are, where all the water systems are, for example. So when you've seen the damage of the earthquake, you can work out where things are going to occur. The second, and absolutely critical, is engineering down the risk. If you had an earthquake of, let us say, 7.5 in central Tokyo, or in many areas such as Haiti, which have got much less good engineering standards, the loss of life would be massively greater in the area of lower income. Good engineering, knowing an earthquake's going to occur, can engineer down the risk very substantially. And engineers can say, this building is not earthquake-proof, but it's proof against something for, it's a 100-year type event, it's a 1,000-year type event, and you can particularly concentrate on making sure that big public buildings like schools, hospitals, areas people are going to congregate are protected, and therefore loss of life will be minimised. So there are things you can do in the immediate term, medium-term predictable things, and then the long term is largely an engineering challenge, but one which we know works. So that's earthquakes. Moving on to, and the second two I'll do in slightly shorter time, because earthquakes are some of the most common. Moving on to tsunamis. Tsunamis are big waves, and I think, again, everyone will be aware of them. Roughly 80% of them are from earthquakes, some of them for volcanoes or landslides, and in the deep past, and no doubt in the hopefully deep future, asteroids hitting water, rather like a pebble being dropped into a pool, cause massive waves that can occur outside them. What you get then is a long wave, and it's very different to the waves that you normally see in the sea, which just occur in the surface area driven by the wind. These are waves that go through the entire water column, and they move extraordinarily fast. So they can go up to 800 or 1,000 kilometers an hour in terms of their speed of movement. But if you're on a boat on top of them, you'd hardly notice it. The issue comes when it starts to get close to land. And again, people who've done physics recently will recognize this phenomenon. As it gets shallower, the wave slows down and it gets bigger. And it can grow to a very large wave indeed. Anywhere between 3 and 30 meters would be perfectly typical for a major tsunami. I'll put a sense of scale for that in a second. They are immensely powerful when they hit land, and up to no more than 15 centimeters of water moving at the speed they will move is quite capable of knocking an adult off their feet. So don't be sort of fooled by the fact it doesn't look terribly deep initially. The most extreme recent example of this, and it was a huge tragedy of its era and still has implications now, was the Boxing Day tsunami of 2004. So this is actually still under 20 years ago. This is a large earthquake, 9.1 earthquake, and it occurred 30 kilometers below sea level. So quite deep, actually, as compared to where we are off Indonesia. It killed over the next days and weeks probably just shy of 228,000 people, this wave. So massive loss of life in 14 countries because it spread out from its initial epicenter. Waves were up to 30 meters high, which is high, just to look up, to think about this. And it spread across the Indian Ocean, hitting India a couple of hours later, and Africa, and I'll show this in terms of numbers, about 7 hours later. So that scale on the right is just to give you a sense of what a 10-meter wave is like compared to you, and 30 meters, of course, is 3 times higher than that. So these are big. If you're in a potentially low-lying area, the things to watch out for are shaking of the earth of any sort, the sea going out a long way very suddenly, or a tsunami warning on your phone. And as a result of this, there's much more careful mapping out tsunamis and tsunami warnings, particularly in the Pacific area. If any of these occur, get to high ground fast. So the tsunami that occurred in Indonesia was the largest one in recorded history, but they've occurred multiple times through history. They're most well described in Japan, which actually named tsunamis. But you can also get tsunamis occurring in Europe, and I've just chosen the Lisbon tsunami of 1755. So this was a major earthquake followed by a tsunami, and the tsunami went through Portugal, out to the Azores, went along North Africa, France, and actually hit Cornwall, where it was described as having a wave of about 3 meters, still very large, and great loss of life. Numbers are not clear. So you can certainly get tsunamis affecting here. In deeper history, we've had very major tsunamis occurring in the UK, for example, from landslides in Norway, falling off large mountains. The Canary Islands, in theory, could cause a tsunami at the other side of the UK. So any country that has got a coast potentially is at risk of tsunami from somewhere else. The risks to health from tsunamis overlap with, but are not absolutely identical with, those from an earthquake. Of course, the biggest difference is drowning. People caught in this incredibly fast-moving water are highly likely to be at risk of drowning. You can also get trauma from debris if you're floating through the water at great speed and you're hit by something. Trauma occurs just as easily as it does from something falling from a great height. And just to give you some sense of scale of the force of these, that is a 2,600-ton vessel carried 2 to 3 kilometers inland by the tsunami. So these things have got enormous power. And then you can get infection from contaminated waters because it will flood all the water things. So basically what you're swimming around in is diluted sewage. So this is an additional risk as well. Longer term, you're going to get destruction of safe water and sanitation for some time. They'll all be flooded and many will be destroyed. Because you've got lots of pools of water, it's an ideal breeding ground for many vectors, mosquitoes in particular. So if dengue or malaria are a risk locally, the likelihood is you're going to get those occurring, and massive destruction of homes and livelihoods. This is the one bit of first aid I thought I'd talk about, just because I think it's very important for everybody to feel comfortable dealing with drowning. Well, comfortable is too strong a word, but feel they know at least what to do. And the answer is it's a relatively straightforward thing. Those of you who've done St John's Ambulance or other training in first aid will recognise this. If someone has drowned, whether it's falling into a river or hit by a tsunami, important to do CPR compressions where you pump on the chest. Much bigger pumping if you've got an adult, smaller if you've got a very small child, but the basic principle is the same. And you do 30 chest compressions and then 2 breaths 5 initial breaths, 30 chest compressions, 2 breaths in, and then just repeat that in a cycle. And if they vomit, roll them on their side. That's basically the first aid for drowning. But drowning is something from which people can recover if people respond to them rapidly. Many emergencies are, of course, complex and bring several things together. And at the last talk I gave on nuclear and radiological emergencies, I talked about the Fukushima disaster, and that was an example of an earthquake which shut down the system, damaged it to some degree, but that worked as it was intended. Then there was a tsunami due to the earthquake, and that flooded the nuclear power station, and that led to a hydrogen build-up, led to an explosion, led to a release of nuclear material. So things are often complicated by the long-term effects of earthquakes or tsunamis. This had, fortunately, relatively low health impacts, but it could have been a lot worse. Finally, volcanoes. There are about 1,500 active volcanoes on Earth in total, many of them in beautiful and obscure places, but many are nearer human habitation. In Europe, there are currently 82 volcanoes that are recognised, but volcanoes can come and go, as you have probably seen recently in Iceland. They occur near tectonic plates, which are either converging, coming together, or diverging, pulling apart in the main. You have very significant risks if you're close to a volcano when it goes off, possibly unsurprisingly, but some of them are more obvious than others. But they can also cause risks over distance. And earthquakes cause risks over distance because of shaking of the earth, which the bigger the earthquake, the further out it goes. Tsunamis cause risks due to a wave hitting, which can travel over many thousands of kilometers. Volcanoes cause risks principally through the air, through material that is spewed up into the atmosphere. So there are multiple volcano types. I'm not going to go through all of them. I'm just noting that there are lots of different types of volcanoes, and they have slightly different ratios of risk or substantially different risks between them. But there are predictable risks that are near a volcano, depending on the type. The type will determine which is the most likely. The first and the most obvious is lava flow. It is spectacular. It's certainly incredibly hot. If you got hit by that, then you're a goner. But they do move quite slowly. So they're predictable, coming down at a speed which humans can usually get out of the way. Much less easy to escape if you're nearby is tephra. And that's a combination of ash through to pumice stones being thrown up into the air and dropping on you from a great height. And this can be, ash sounds trivial, but the volumes of it can be absolutely vast, and they can land on people, they can suffocate people, they can land on buildings and collapse buildings. And the most famous of these is the town of Herculaneum, buried under ash after the eruption of Vesuvius in 79 AD. So ash can be very destructive immediately around. The ones that are probably less widely recognised by people who've not sort of thought about it are these ones. The first one is something called pyroclastic flow. This is hot gases and material rolling down a mountain at extraordinary speeds. So they can go over 100 kilometers an hour, well beyond what you can obviously outrun or even outdrive, and they will be very hot, 100 to 600 degrees centigrade. If they hit you, obviously you're in deep trouble. Lahars, volcanic debris and water, mud flowing at tens of kilometers, and they can again be very destructive. So on the right is a lahar that occurred after the volcano Montserrat, and as you can see, it basically buried everything in its path in mud at considerable speed and caused a lot of destruction. You can also get glacial outbursts, and you can get landslides. So there's a variety of ways in which essentially gravity moving at speed can hit you in the immediate vicinity of a volcano. But the things which cause the damage over the longer distance are gases. And volcanoes release very significant numbers of gases depending on the volcano type. Includes carbon dioxide, hydrogen chloride, hydrogen fluoride. These are all dangerous gases. Again, as many of you will know, hydrogen sulfide, sulfur dioxide. In large quantities, all of these are dangerous through to deadly. They're heavier than air, so they tend to pool in lower areas. So if you're near a volcano, you're feeling unwell, get up into a higher land away from where these may be pooling. And they can travel long distances. So this is an example. The volcanic eruption in 2010 in Iceland spread ash which travelled all around Europe. Fortunately, it did relatively little health harm, although it did close airspace over Europe for long periods of time. And you can see the size of the ash cloud by seeing that globe at the bottom done by the Met Office and the photograph from NASA. So the gases can move over considerable distances. And if you have one of the more dangerous gases is part of the eruption, which many eruptions can do, these can travel the same sorts of distances. So here's an example that affected the UK. This is the Laki eruption in Iceland in the 1780s. It erupted for over 8 months. Important point to remember. People think volcanoes just erupt once, that's it, done. Actually, they can erupt over long periods, months or years in some cases. Hydrofluoric acid and sulfur dioxide were contaminated all of Iceland and led to the destruction of almost of the majority of the livestock, over 50% of all the livestock, leading to famine. So they had a big local effect in farming terms. But they also spread over all of Europe. Probably the only estimate that we have is that probably about 23,000 people in the UK died of sulfur dioxide poisoning as a result of a volcano in Iceland. So these can travel over long distances. Particularly if you've got something like asthma, or if you've got cardiovascular diseases, a variety of other things, sulfur dioxide can be fatal. It also had a wider effect globally, leading to a global drop in temperature, and probably affected monsoons around the world, including Africa and Asia, leading to famines. So this is an example of a European volcano. Here are some other volcanoes. Again, I'm not going to read them out, but giving you some understanding of the fact that tens or hundreds of thousands of people can be killed when volcanoes erupt by a combination of the immediate effects around the volcano and the longer-term effects of the gases elsewhere. And if they don't kill people, they can certainly change the landscape and change the environment. For example, Montserrat, which erupted in the 1990s, led to 2/3 of the population leaving the island. And then the longer-term health effects of volcanoes have some similarities. First thing, again, to repeat, volcanoes can erupt over months to years, so this may be something which is going to be a long-term effect. They can have a direct effects on health, but they can have indirect effects also by their effect on the weather, on agriculture, and on people's psychological states. They can lead to people having, again, very serious concerns, particularly if they live in that area. They can have an impact on climate, which is short or medium term, and that can in turn lead to knock-on effects in climate-driven areas of agriculture. and they can lead to long-term psychological effects. So to summarise, the geophysical emergencies of the Earth suddenly moving, earthquakes, tsunamis and volcanoes, sudden, largely unpredictable as to when, although with a fair degree of predictability as to where. They can cause massive loss of life very suddenly. So I've given you examples of all three of those where the numbers of people who died in the event were over 100,000. Sudden deaths over a very short period of time. They can then have an immediate effect on infections, nutrition, preventative and curative services, which can go on for months to years and potentially intergenerationally. So you need to plan for this. The emergency is not over when the immediate people have been rescued or not, and long-term effects on shelter and on infrastructure and profound health impacts as a result of people becoming poorer. So these have big impacts, big health impacts, and I think when you understand them, it makes it easier to understand what you need to do to respond to them, and particularly in the case of earthquakes, to make it less likely there'll be future loss of life on this scale. Thank you very much.
Thank you, Chris. It's really tempting to say, I hope the Earth moved for you like it did for the rest of us. There's a couple of interesting questions. First one follows on from your last couple of slides, which is, are there any data on long-term cancer cases following collapse of buildings, for example, like after what happened at 9/11? But, some of the massive trauma on these terrible building materials that have cropped up. What's known about the long-term consequences?
So in a sense, there's very weak direct data where people can just trace it through from an earthquake in particular. But I think working from first principles, for example, if there's a lot of asbestos used locally, you can predict that mesothelioma, which is a cancer which occurs after that, is going to be at significantly increased risk. And the same will be true for many of the other toxic materials you can get, which people can be exposed to. But I think it's important to put them in context. In the context of the kind of massive earthquake which we're talking about, this will be a very fractional thing. And if you compare it to someone's lifetime cancer risk, it's likely to actually be a very small fraction of their lifetime cancer risk. So I think that the general question is entirely reasonable, but in relative terms, it's going to be a relatively small part of the risk here.
The sort of public health stroke planning that springs to mind after this is, you pretty well know roughly where earthquakes can happen. Some are more likely to happen in some places than others, and you know where the volcanoes are. So if you're in charge, say, of the United Nations, where are you going to put your resources to be ready? And who's going to finance that, and how's it going to get there?
That's multiple questions.
Yeah.
And I think that exaggerates the authority of the United Nations to be able to actually make these kind of big decisions. But what would you want? What do we collectively want to do? I think that the biggest, given that earthquakes are the biggest risk, the first thing you want to do is map out where they're likely, and where there is a large population, and then you want to deal with the engineering. We really should be aiming in particular for the big public buildings, and I'm taking schools as an example. If the odd cowshed falls down, that's a shame, but actually what you really need to do is strengthen those buildings. We know how to do it. If you look at what happens during quite significant earthquakes in Japan, there really is minimal damage because they've been engineered not to be damaged themselves and to damage humans when they occur. So I think that would be the first thing. The second thing is we need to strengthen the infrastructure in these kind of areas so that it doesn't predictably all get destroyed, and you have several different routes in for things like water in particular, power to a lesser extent, and to have standby resources elsewhere. And in the case of tsunamis, we need to have what we now have much better, which is early warning systems. They're not going to help the people in the immediate vicinity of a tsunami, but they should be able to give people warning who are an hour, 2 hours away from a wave to get onto high land and get away from the risk. So I think those are all technical answers. Of course, the big geopolitical answer is that the biggest damage tends to occur in areas of poverty. So wealthy nations are not immune from these at all, but it is going to be easier for them both to engineer out the risk and to recover from the hit when it occurs. So that's a sort of longer-term development aim.
There's a very beautiful support dog sitting at the front down here. And a good question. Can animals predict the movement of the Earth's crust or the...
There's a lot of rather anecdotal, but probably quite convincing anecdotal information that animals start responding in a rational way in advance of things happening. So probably the answer is yes. But seeing animals moving around very quickly, I think, doesn't mean that an earthquake's coming. So I think this is something which I would be very cautious about that, drawing that conclusion.
Let's take some questions from the floor.
What I want to ask you is, which came first, the tectonic plates, earthquakes, or the continental drift? Or is there any connection between the two?
Well, I think most people try and understand earthquakes in the context of tectonic plates moving around, which they've done for the pretty well indefinite past. It's not quite to the indefinite past, and will do for the rest of time. Of course, the configuration of the Earth and what the Earth looks like in terms of its continents has shifted hugely over time, but much less over human time. So in the times humans have been around, it looks more like where we are at the moment. The continents are moving around very slowly, but the tectonic plates, they're often moving a few millimeters to centimeters a year, but if that builds up over decades or centuries, you're talking about very, very strong forces over very large distances. Some of the Himalayan tectonic plates have been moving very gradually for over 300 years and have not had an earthquake. Sooner or later, that energy will have to be released, for example, and that will predictably lead to a very significant earthquake, hopefully not one with a large loss of life.
So there is a connection?
Yes, at one level, yes.
The significance of transversal longitudinal waves in earthquakes, is there much difference in the intensity of the effect?
Well, I think the strength of them, as you say, sense the direction of them and the amplitude of them in terms of how big or small, are they shaking very fast or slightly longer waves, will have big implications as to which buildings get knocked down. In Kathmandu, for example, many of the taller buildings got knocked down because of the particular amplitude that you had in that earthquake. Had it been a different amplitude, it might have been some other lower buildings. So it does have implications, but each earthquake is different in that respect.
You mentioned about maternity care a couple of times in your secondary health impacts, and I wondered if you had any views or commentary on other kind of differential impacts to men, women, children in any of the health consequences.
So there are. I mean, this will depend partly on societal things, and I think every society is slightly different on this. There are some predictable ones, though, and I think maternity services is obviously one. If all the hospitals are knocked down, if all the health services stop, when people have a baby is not something which can be, changed. That's going to happen. The other one that's very predictable is children, because if they're at school and the schools fall down, that has an enormous implication. So age and gender can both have significant effects. It also can have effects, for example, if one gender is more likely to be in the home and the other out in the field, that also can have effects, and so on. But these are, in a sense, social constructs, whereas the age and the maternity ones, I think, will be universal.
Are there mechanisms within the UK for sending out teams in an organised way to places where this happened? We see groups of cavers and so on rushing out, and people are trapped in caves. How does it work?
Yeah, so obviously the greatest expertise in earthquakes tends to be in countries which are earthquake prone. They tend to have a lot of local capacity. But many countries, including the UK, have people who have learnt a lot of skills about earthquakes and who will fly into an earthquake zone, particularly in the initial period, when actually you need this highly technical either kit or, for example, sniffer dogs or whatever, bring them in for a period of time. You're not going to find many people surviving under rubble much outside a week. So this kind of effect is a relatively early effect. The longer-term effects tend to be much more generic health ones, or the management of crush injuries and management of kidney failure in particular is something many low-income countries would have difficulty with, and you need to bring that capacity in to help them.
Well, I think you've stunned them into silence, Chris. Professor Chris Whitty, thank you very much for talking to us this week.